There are two types of waves, transverse waves and longitudinal waves, where waves are something that transfer energy between 2 points. In a transverse wave, the particles vibrate at right angles to the direction of travel, and an example of a transverse wave is visible light. For a longitudinal wave, the particles vibrate parallel to the direction of travel. An example of a longitudinal wave is a sound wave. There are several key properties of waves. The rest position is the point on the wave where the particle is undisturbed and not vibrating. The peak of a wave is its highest point above the rest position, and conversely, the trough of a wave is its lowest point beneath the rest position. The amplitude, A, is the maximum displacement from a point along the wave to its rest position, and the wavelength, lambda, is the distance between a point on one wave to the same point on another wave. For example, from peak of wave 1 to peak of wave 2, or trough to trough of the same waves. The wavelength is denoted by the Greek symbol lambda. The time period, t, is the length of time in seconds it takes for a wave to complete one full cycle from peak to peak or trough to trough. The frequency, f, is the number of waves produced per second. Also, it's the number of waves which pass a specific point per second. When there is a boundary between two materials, waves can be reflected at this boundary. We measure the angle of incidence as the angle between the incident ray and the normal, which is the line perpendicular to the surface, and the angle of reflection as the angle between the normal and the reflected ray. The law of reflection is that the angle of incidence is equal to the angle of reflection. Here, these angles are 45 degrees. With this flat mirror, the image is upright and virtual. This is how we see a virtual image. As the rays seem to diverge from behind the mirror, the image of the apple appears to come from behind the mirror. Waves change speed when they pass across a boundary between two substances with different densities. This causes them to change direction, and this effect is known as refraction. Here, the refractive index of glass is greater than the refractive index of air. As shown by the diagram, this means that the refracted ray bends towards the normal. This is because it slows down upon entering the medium. Snell's law states that n1 sine θ1 is equal to n2 sine θ2. Therefore, you can calculate the angles or refractive indexes if you know 3 of the other values. The electromagnetic spectrum is split into 7 different regions, each with different properties. To the left are regions of long wavelength and short frequencies. Radio waves have the longest wavelength, followed by microwaves, and then infrared radiation. In the middle is the region of visible light, which is only a few hundred nanometers wide. To the right are regions of shorter wavelength and high frequencies. Gamma waves have the highest frequency, followed by X-rays and ultraviolet waves. Waves with higher frequencies have more energy, so a gamma ray has more energy than a radio wave. When two waves meet, they overlap with each other. This results in a third wave, which is the sum of the displacements of the original 2 waves, which is caused by superposition. However, superposition isn't limited to only 2 waves, but can be the merging of many more. Any position above the rest position is a positive displacement, whilst any position below the rest position is a negative displacement. Just like addition and subtraction of numbers, a positive plus a positive results in a greater overall displacement and therefore a greater amplitude. The same applies for the negative displacements being summed, while a positive plus a negative results in a smaller amplitude or possibly no amplitude at all. So, if you have 2 waves at the same position at a point in time superimposed upon each other, there will be constructive interference, meaning that the amplitude of the wave of the sum of the waves will be double the amplitude of each of the initial waves. However, if they are half a wavelength out of phase, they would be destructively interfering with one another, and therefore the amplitude would be reduced to 0. When the waves are between 0 to a half a wavelength out of phase with each other, the superposition of the waves creates a mix of constructive and destructive interference which causes an odd-shaped wave.